Hello everyone, welcome to Calculus Lecture 13. And today is going to be all about solids of revolution. Seems like there's a thunderstorm. I'm not sure if you can hear that. That's just thunder on my end. So let's talk about solids of revolution, which is what today's lecture is all about. So basically what we're going to be doing is and I mentioned this last time, so you'll already kind of know what I'm talking about if you watched the last lecture. But basically, we're going to have some sort of function. And we're going to be forming a solid by rotating it around the x-axis. Like so. And you can sort of imagine what the solid will look like. And then the question is, we want to find the volume of that solid. So the way we're going to do this is not by integrating the function itself, because that just gives us an area. But what we're actually going to do is we're going to integrate the areas of the cross sections. So at any point x, we can find the area of the cross section, which is a circle, because we know the radius is just the value of the function. So the radius at any point is just f of x. And so the area of the cross section at x is the radius times the radius squared times pi, which is just pi times f of x squared. And then we're just going to go ahead and integrate that. So this particular graph is the graph of x to the 1/2. And let's just say this number is 2. So we're going from 0 to 2. All right, so we want to find this volume. So then we're just going to integrate from 0 to 2. We're going to take the integral of pi times f of x squared. So that's pi times f of x is x to the 1/2. So when you square it, that's x. And now we know how to do this. So this is pi times x squared over 2 from 0 to 2. At 0, it's just going to be 0. That doesn't matter. And so we're just going to be taking the value at 2. So that's pi times 2 squared over 2, which is 2 pi. And that's going to be our volume. So let's do another one. Let's find the volume of a solid formed by revolving the equation or the curve y equals negative x plus 1 around the x-axis. I'm going to say from 0 to 1. So I'll just pause for a moment so you can try and solve this on your own, and then I'll go over the answer in just a minute. All right, so let's see what this is. So again, the area of the cross section is just given by the same formula as before. That's pi times f of x squared, which is what we're going to be integrating. So this is the integral from 0 to 1 of pi times y squared dx times negative x plus 1 squared dx. In this case, 2 is a reasonably small power, so I'm just going to do this by expanding out. All right, so negative x plus 1 squared is x squared minus 2x plus 1. I'm going to also pull the pi out of the integral, just to make things simpler. And then I can just integrate each part separately using the power rule, and then apply the fundamental theorem of calculus. So the x squared is going to give me an x cubed over 3 term. The minus 2x gives me a minus x squared, and then the 1 just gives me x. And then I'm going to go from 0 to 1. So actually at 0, all of this is going to be 0, so I don't need to worry about that. So I'm just going to evaluate at 1. So this is pi times 1/3 minus 1 plus 1. And that's just going to be pi over 3, which is our final volume. Let's do another one. Let's do, all right, so find the volume of the solid formed by revolving the about the x-axis the region bounded by the graphs y equals e to the x between x equals 0 and x equals 1. So this is a common format you might see in a test. It'll tell you to find the volume bounded by this region, so don't be fooled by that. The x equals 0 and x equals 1 are just your endpoints. That just means you're integrating from 0 to 1. All right, so I'm just going to pause for a moment, see if you can solve that, and then I'll give the answer in a few minutes. All right, so let's see what this answer is. So we're just going to have our integral from 0 to 1 of pi times e to the x squared, so that's e to the 2x dx. All right, so what's an antiderivative of e to the 2x? So remember the derivative of e to the 2x, it's going to be 2e to the 2x. So I'm just going to divide that by 2, and so 1/2 e to the 2x is going to be an antiderivative for e to the 2x. And we're just going from 1 to 0. So that's going to be pi over 2 times e to the 2 minus e to the 0, so just minus 1. And that's going to be our final answer. All right, here is some more challenging question. You're going to need to think a bit critically for this. So I'm going to have a function y equals x squared. And I'm going to just say this is the point 2, 4. Now, instead of rotating this all the way around the x-axis, what I actually want to do is rotate it around the y-axis. So I'm going to rotate this way. And then the question is, what's the area of that solid? I'm going to pause for a couple of minutes, see if you can try and figure this out, or at least write down an expression for what the answer might be. All right, so I'm basically going to do the same thing I did before, but now remember this width is not the square, right? So if this is some value of y, then at this point x comma y is x comma x squared, which is y. So the x value is the square root of y, which means that this distance is the square root of y, not the square. But now I'm going to integrate the same way. I'm just going to go from 0 to 4 of pi times the square root of y squared dy. The variables are different, but that's okay. And the square root of y squared is just y, which is actually even nicer than if we were rotating around the x-axis. So that's the integral from 0 to 4 of pi y dy. That's pi y squared over 2 from 0 to 4, which is pi times 4 squared over 2, which is pi times 8. So that's 8 pi. And that's going to be our final answer. Now, we could also be asked to find a solid of revolution bounded by two functions. So what we can have is a function that looks like this and a function that looks like this. And we could be asked to find the volume when just this region is rotated around the x-axis. So basically the way we're going to do that is we're going to find both the volumes, the outer region and the inner region, and we're just going to subtract them. Now, we have to be careful. So remember when you were asked for the region bounded by 2 points, you're going from 0 to the point where they intersect, some point x. And the first thing you want to do is find that point x. Okay, so in this case, this function here is f of x equals the square root of x, or x to the 1/2, and g of x equals x. So I'm just going to leave that up for a moment, see if you can try and figure out what that volume would be, or at least a formula for how you might find that volume. All right, so let's do this. So there are three things we're going to need to do. First, we want to find that point of intersection. Then second, we want to find the volume when you rotate the outer region. And we want to find the volume when you rotate the inner region. And then we need to subtract them. So what is this point of intersection? Well, the points intersect when f of x equals g of x. And we can see from the graph it's a positive value we're looking for. So we want the square root of x to equal x. So I'm just gonna square both sides. So x equals x squared. And the solutions to this are going to be 0 and 1. Well, you don't want 0, we want the strictly positive solution, so we're just going to take x equals 1. And that's going to be the point we're looking for. All right, and then once we have that, we know we're integrating from 0 to 1. So let's first do f of x, because that's the outer function. We can see that from the graph. So now we're going to go 0 to 1, f pi times f of x squared dx. And then we're going to subtract the integral from 0 to 1 of pi times g of x squared dx. So that's the inner thing. And then once we do that, that'll give us the volume of the region bounded by the two functions. So let's work this out. So f of x equals the square root of x and g of x equals x. So this is the integral from 0 to 1 of pi times the square root of x squared. So that's just x dx. Minus, and I'm just going to combine them because the bounds are the same, so we can just put them in one interval. And the pi is also the same, so I'm just going to put that with parentheses. And g of x is x, so g of x squared is x squared. Oh, and let me just move the dx out since I'm, so this is x minus x squared dx. And now we can work this out, so that's pi times the integral from 0 to 1 of x minus x squared dx. Which is pi times x squared over 2 minus x cubed over 3, going from 0 to 1. And with 0, of course, this whole thing is 0, so we just need to evaluate at 1. So that's pi times 1/2 minus 1/3, which is pi over 6. And that'll be our volume that's bounded by those two functions. So let's do a couple more examples. All right, so here's one. We're going to have, in this one, we're actually being told what the bound is. But this is going to be another example of rotation around the y-axis. So we're going to have 0 here. This is going to be 4. And this is going to be g of x, which is 2x squared. And this is going to be f of x, which is x squared. And the question is, what's the area of the region bounded by these two functions when they're rotated around the y-axis between 0 and 4? So we're assuming it's bounded by y equals 4. So I'll pause for a moment, see if you can figure that out. Okay, so in this case, what's going to happen is, again, since we're rotating around the y-axis, given some value of y, we need to find this length. And basically to do that, we're taking the inverse function. So if we have some value y, then this length, well, f of x equals x squared, so this is going to have to invert that, and this is going to be the square root of y. While g is slightly different, if we have some y, and this is g of y, then we have y equals 2x squared for whatever that x is. So x is going to be the square root of y over 2. That's a little hard to see. So I'm just going to write it on this side. So that's going to be the square root of y over 2. And so those are going to be the radii that we're going to use when we do the integrals. So now we're going to have the integral from 0 to 4 of pi times, I'm just putting this all in one integral. First you're going to have f of x squared, not f of x squared, but f inverse of x squared. So the square root of y squared, which is just y, minus the g integral. So that's going to be this thing squared. So that's just y over 2 dy. And then we can work out this integral. So that's going to be pi times y squared over 2 minus y squared over 4, going from 0 to 4. And we'll plug that in. So that's pi times 4 squared over 2 minus 4 squared over 4. This should be giving us 8 minus 4 is 4, so that's just going to be 4 pi. And that's going to be our final result. All right, let's do one more example. Let's find, so let's rotate around the x-axis. We're going to have two functions, x cubed. I'm trying to draw this properly. It's a little bit flat at the beginning. X cubed and x to the 4th. I think this goes like this. So x cubed and x to the 4th. So I want to find the area when this is rotated, or the volume when this is rotated around the x-axis. I'll pause for a minute, see if you can figure that out. All right, so let's do it. So we know that the point where x cubed equals x to the 4th is just at x equals 1. All right, so we're going to be going from 0 to 1. Now, we're still going to have our pi, and then we're going to be subtracting two things. Now, between 0 and 1, when we have our x is smaller than 1 in absolute value, x cubed is going to be bigger than x to the 4th, because multiplying by something smaller than 1 makes your number small. So we're going to have x cubed come first, so x cubed squared minus x to the 4th squared dx. All right, so that's the integral from 0 to 1. Pi times x to the 6th minus x to the 8th. And we know how to do this, so that's pi times x to the 7 over 7 minus x to the 9 over 9. going from 0 to 1, which is pi times 1/7 minus 1/9. And that's like 2 pi over 63. And that would be our final answer. So we've finished all the examples for this section. This was a pretty short chapter. So let's talk a little about what we'll do next time. So we're going to do some very important theorems next time. We're going to be talking about the mean value theorem, Rolle's theorem, the intermediate and extreme value theorems. So let me just define those, and we can do a few examples if there's time. And I'll define these all again next time, so don't worry about it. But so that's the intermediate value theorem, the extreme value theorem, mean value theorem, and Rolle's theorem, which we'll see is just a special case of the mean value theorem. So I'm actually going to state Rolle's theorem first. So what Rolle's theorem tells us, and I'll write down the actual formulas next time, but I'm just going to do it with a picture today, is if we have some differentiable function, let's call this f, and f takes the same value at two different points, right? So the y value at these points is the same. Then there's some point between these two where the derivative is 0, which sort of makes sense. We're saying that the tangent line is horizontal, which makes sense because assuming the function isn't constant, if it's constant, then the derivative is 0 everywhere, so we don't have to worry about that. But if it's not constant, it's going to increase, but then it has to decrease back to be able to be the same point at the second value. And when it changes from increasing to decreasing, or decreasing to increasing, we have a local maximum or minimum where the derivative will be 0. So that's kind of the intuition for Rolle's theorem. And then the mean value theorem is slightly more general. So that's going to let us choose any 2 points. Let's say we choose this point and this point. Actually, no, I'm just going to choose slightly different points. Let's go with this point and this point, just to illustrate this properly. So then we have some line through the 2 points. Let's see if I can draw that. And say this is A, this is B. So the slope of this line is f of B minus f of A over B minus A. And so the mean value theorem tells us that there's some point in the middle where the derivative equals this value. The derivative equals f of B minus f of A over B minus A. So it's basically telling us that the tangent line is parallel to the line connecting the 2 points, which also sort of makes sense. Now the intermediate, now both the mean value theorem and Rolle's theorem apply to differentiable functions. The derivative has to exist everywhere, otherwise this won't necessarily be true. Now the intermediate and extreme value theorems apply to continuous functions. We don't actually need them to be differentiable. So let's state these. The intermediate value theorem basically tells us if we have any continuous function, so it's even allowed to be pointy, doesn't matter. And we have 2 values that the function takes, y1 and y2, and it has to be continuous on the interval between like these 2 points. And then we pick any value between the two, then the function takes that value as well. So basically it can't like have any holes or skip any values when it's going from y1 to y2. Now the extreme value theorem applies specifically to functions on closed and bounded intervals. So for the extreme value theorem, we're going to have a function on some closed and bounded interval. So closed means it includes the endpoints. Bounded just means it can't go off to infinity. And we have some continuous function on there. Then the function achieves an absolute maximum and an absolute minimum on that interval. And the way you would go about finding this is you want to find all critical points. So that's anywhere where the derivative is 0. Or, well, if it's not differentiable, it's a little bit harder, but assuming it is differentiable, you would find all the critical points. Any point where the derivative is 0, along with the two endpoints, this one and this one, and you would just check the values at all those points. And the smallest one is your absolute minimum. The biggest one is your absolute maximum. So all of these theorems are super useful. We can just do a couple of examples real quick. So say we have the function f of x equals x squared on 0 to 2. Find the value guaranteed by the mean value theorem on this interval. So remember, the mean value theorem guarantees you a point where the derivative of, so some point x, so that the derivative of f at x equals f of b minus f of a over b minus a. And over here, your a is 0 and your b is 2. So see if you can figure that out. And I'll give you the answer in just a few minutes. Okay, so before we find this value of x, we need to know what we're looking for. So we just need to figure out what this value is first. So f of b is f of 2, so 2 squared, which is 4. F of a is 0 squared, which is 0. B is 2, and a is 0. So the whole thing, f of b minus f of a over b minus a, is 4 over 2, which is 2. So we want a value where the derivative is 2. Now, what is the derivative? We can just take the derivative of x squared. So f prime of x equals 2x, and we want 2x equal to 2, so x equals 1. And we can double check that x equals 1 is in this interval. So this is the value we're looking for. Let's just do one more example. Let's find the value guaranteed by the mean value theorem. On the graph of e to the x on the interval from 0 to 1. I'll just pause for a minute. All right, so this is our A, this is our B. So what is f of b minus f of a over b minus a? So f of b is e to the 1, which is e, minus f of a, which is e to the 0, which is 1, over b minus a, which is 1 minus 0, which is just 1. So this is just e minus 1. And so this is telling us there's some value between 0 and 1 where the derivative is e minus 1. Now the derivative of e to the x is e to the x. So we want x so that e to the x equals e minus 1. And so x is going to be the natural log of e minus 1. And for this, actually, you would really just have to use a calculator to check if it's in the interval you're looking for. So if you do use a calculator, you're going to see that the answer is about 0.54. And we can see that that is in the interval 0 to 1, and so that is the point we're looking for. Now, you know there will always be a value, so if you only get one solution, then you do automatically know it's in the interval you're looking for. But it's good to double check just to make sure you didn't make any mistakes. So that's it for today, and we'll just talk more about all this next time.